Welcome to Brain Vision.
In this problem, we're going to talk about Compton scattering. So consider that we have a photon, an incoming photon represented in red in our picture, that collides with an electron. And let's say that uh, the initial wavelength of the photon was lambda, and the electron was initially at rest. So the photon comes out of the collision, scattered by an angle theta, and with a new wavelength lambda prime that is equal to lambda plus h over the mass of the electron times c times 1 minus the cosine of the scattering angle. Okay, so in our problem, we have a photon that has a wavelength of 0.105 nanometers and scatters of an electron with an angle of 60 degrees. And our goal is to find what are the magnitude and direction of the momentum of the outgoing electron. Okay, so first, what I'm going to do is to calculate lambda prime. After calculating lambda prime, I'm going to be able to calculate both the the y component and the x component of the momentum of the outgoing electron. In order to calculate lambda prime, I'm just going to put it into the Compton scattering equation. So we have the lambda prime is lambda plus h over mc times 1 minus cosine of theta. H over mc is is Compton's wavelength, and it's equal to 2.43 times 10 to the minus 12 meters. So I'm going to write this as 0.105 nanometers plus 2.43 times 10 to the minus 3 nanometers times 1 minus cosine of 60. So lambda prime is equal to 0.1062 nanometers. Okay, so notice that now we can apply conservation of linear momentum. So initially, incoming momentum, the momentum of the incoming photon, sorry, was only in the x direction. And here I'm setting a coordinate system such that the x direction is to the right, the y direction is upwards. So the initial momentum of in the x direction is equal to the momentum of the photon, and that's just h over lambda. This is the initial momentum in the x direction. In the y direction, the initial momentum is 0. Okay. Now, the initial momentum in the x direction is equal to the final momentum in the x direction, and notice that the final momentum of the photon in the x direction is h over lambda prime times cosine of theta, while the final momentum of the electron in uh, the x direction is, I'm going to call it just p y prime. Now, in the y direction, we have that 0 is equal to the final momentum of the photon in the y direction. That's h divided by lambda prime times sine of theta minus p y prime. And up here I wrote py prime. It should have been px prime. Sorry for that. So I'm going to start with the second equation. It's easier. So we have py prime is equal to h over lambda prime sine theta. H is 6.63 times 10 to the minus 34 joule second. Lambda prime is 1.062 times 10 to the minus 10 meters times the sine of 60, and that is equal to 5.4 times 10 to the minus 24 kilograms meters per second. And px prime, I'm going to isolate it from the first equation up here. So px prime is h times 1 over lambda minus cosine of theta divided by lambda prime. Um, okay, so this is equal to 6.63 times 10 to the minus 34 joule second times 1 over 1.05 times 10 to the minus 10 meters minus cosine of 60 over 1.06 2 times 10 to the minus 10 meters. And this is equal to 3.2 times 10 to the minus 24 kilograms meters per second. So the total momentum, the final momentum of the electron, is equal to the square root of px prime squared plus py prime squared. So this is the square root of 5.4 times 10 to the minus 24 kilograms meters per second squared plus 3.2 times 10 to the minus 24 kilograms meters per second squared. So P prime is equal to 6.3 times 10 to the minus 24 kilograms meters per second. This is the magnitude, and now we also have to find the direction. Notice that um, the electron is scattered below the horizontal by an angle theta, such that the tangent of theta is equal to the magnitude of py prime divided by px prime. So theta is the arc tangent of py prime, that's 5.4 times 10 to the minus 24 divided by 3.2 times 10 to the minus 24. So I'm just going to omit the 10 to the minus 24. And phi is equal to 59.4 degrees, which concludes our exercise.